Welcome to The Explainer. So today we're going to dive into a technology that's literally all around you, but you can't see it, you can't hear it. It guides robots, it keeps your car from bumping into things, and it's even making our cities smarter. Okay, let's start with something you've probably experienced. You're backing into a parking spot, right? And your car starts beeping. Just a slow beep, then it gets faster and faster until it's just this one solid tone. How in the world does it know exactly where that wall is? And the answer, well, it's not magic, but it sure feels like it, right? It's a technology that gives machines a sense that we just don't have.
What we're talking about here are ultrasonic sensors. They use sound waves that are at such a high frequency, way above what our human ears can pick up, to basically map out and measure the world around them. And they do it all without ever touching a thing.
Okay, so let's get into the core idea. And you might be surprised because it's based on an experience that I bet a lot of us have already had. Picture this. You're at the edge of a huge canyon. You yell out, hello, and a moment later, you hear it. That faint hello bouncing back. Now, if you knew the speed of sound, you could totally figure out how far away that other canyon wall is just based on that delay. Ultrasonic sensors are doing exactly that, just, thousands of times a second. So the big question is, how does the sensor take that tiny little high-frequency echo and turn it into a super precise measurement for a robot or a car? Well, it all comes down to a process that's kind of like a high-tech stopwatch. This whole process is called time of flight, or TOF, if you want to be quick about it. And it happens in 5 super fast steps. First, the sensor sends out a little blip of sound. Second, that sound zooms through the air. 3, it hits an object and bounces off. 4, it comes back and is heard by the sensor. And finally, 5, the sensor's little brain does a quick bit of math, all in the blink of an eye. And the math behind it? It's actually really straightforward. The sensor just multiplies the speed of sound by how long it took for that echo to get back. But now, here's the really clever part. It divides the whole thing by 2. Why? Well, think about it. The time it measured was for the round trip, the sound going out and then coming back. We just want the distance one way, right? So simple, but totally brilliant. Okay, so the secret sauce, the thing that makes this whole show run, is something called a piezoelectric transducer. It's a special kind of crystal that has this amazing dual personality. You zap it with electricity, it vibrates and makes the sound pulse. But then, when the returning echo hits it, it generates electricity. It's the speaker and the microphone, all rolled into one tiny little component. All right, so now that we know how it works, where do we actually see this stuff in action? Well, it's probably in more places than you think. I mean, seriously, by 2025, these things are everywhere. They're the reason your car's parking assist and blind spot monitors work. They're how a smart city knows the trash cans need emptying. They're crucial for measuring liquid levels in giant factory tanks. And they are the unsung heroes helping robots and drones navigate without crashing into everything. But here's a key thing to remember. One size does not fit all. Different jobs need different frequencies. For your car bumper, something around 40 kilohertz gets the job done. It's a great balance of range and cost. But if you're talking about medical imaging, whoa, we're jumping into the millions of hertz. You need that crazy high frequency to get the resolution to actually see inside the human body. Okay, but let's be real. No tech is perfect, right? So to really get the full picture, we gotta look at where these sensors shine and where they kind of stumble. So their biggest superpower is something engineers call material independence. And what that really means is, unlike a camera that uses light, these sensors don't care if an object is clear glass, shiny chrome, or pitch black. Sound just bounces off all of it. They're also rock stars in places that are dusty or smoky, conditions where a regular camera would be completely blind. But like every superhero, they do have a weakness, a sort of kryptonite, a few specific situations that can really throw them for a loop. So here's what you've got to watch out for. First, right up close, there's a little blind spot. They call it the dead zone. Then you've got really soft, fluffy stuff, like foam or thick carpet. That stuff can actually absorb the sound instead of bouncing it back, which basically makes the object invisible to the sensor. And finally, their accuracy can be affected by big temperature shifts and other loud, high-pitched noises in the area, like from a hissing air hose. So you might be thinking, okay, with those weaknesses, how come this tech is more popular now than ever before? Well, the answer is all about modern brain power, digital brain power. Today's sensors are packing some serious smarts. They use these advanced algorithms, it's called digital signal processing, to basically filter out all that background noise and lock onto their own echo. A lot of them even have tiny thermometers built right in to adjust for temperature on the fly. And the really cool part? They can coordinate with each other to avoid getting their signals crossed. That's how you can have a whole fleet of warehouse robots zipping around without confusing each other. It's what makes them so incredibly reliable today. And that reliability goes all the way down to the nuts and bolts, or in this case, the wires. For a big factory, you've got this super tough, standardized 3-wire setup that's built to last. But for someone like you or me, a hobbyist building a robot in the garage, there's a super simple 4-pin version that's just about plug and play. It's the same amazing tech, just packaged for 2 totally different worlds. So, at the end of the day, ultrasonic sensors give machines a new sense, a way to hear an obstacle. It's simple, but it's powerful. And it leaves us with one last question to chew on. We've taught our machines to hear. What happens when we teach them to truly understand what they're hearing?